skyscrapers that spin, blades carving the wind, giant turbines are some of our most impressive machines. If you can get them to work. On Fact Channels, we're untangling the puzzles behind these whirling powerhouses, from stubborn weather to sky-high engineering hurdles. Why is harnessing a breeze so difficult? Stick around for a peek inside one of modern energy's toughest balancing acts. In the open stretches of the North Sea, where fierce storms whip waves into mountains and the sky appears endless, engineers have built forests of colossal wind turbines. Silent sentinels spinning ceaselessly against the horizon. But these mechanical giants face far more than the fury of nature. At the heart of every turbine lies a battle against fatigue. Each rotation is a testament to materials science. Steel alloys and composite blades wrestle with relentless flexing, over 200 million cycles in a turbine's lifetime, demanding inventions that can outlast not just weather, but time itself. Picture this. A single blade on a modern offshore turbine stretches longer than the wingspan of an Airbus A380. The challenge isn't only to make it light and strong, it's to ensure each cubic centimeter of material is flawless, or else cracks less than a millimeter across can spread and doom the entire structure. Some of the most remote wind farms are serviced by helicopter-borne technicians who dangle hundreds of meters above icy seas. The cost of 1 hour of downtime for these turbines? Upwards of $10,000. Repairs must be swift, precise, and performed in treacherous winds that threaten to ground even the bravest crews. Imagine harnessing wind that shrieks at 100 kilometers per hour, yet preventing blades from spinning themselves apart. Turbines employ advanced pitch control systems, motors and algorithms working in unison, to feather their blades like giant mechanical birds constantly adapting to invisible currents. One revelation surprised even industry veterans. Ice accretion can cause catastrophic imbalance on rotors, so engineers turn to technology inspired by jet aircraft, embedding electric heating elements inside blades, melting ice before it ever forms, all powered by a fraction of the energy they produce. The pursuit of ever larger turbines exposed an unexpected challenge. Transportation. Moving a 90-meter blade through narrow mountain passes or centuries-old European villages sparks logistical ingenuity. Modular designs split blades into sections that snap together like Lego bricks atop windy hillsides. Wind doesn't always blow when humanity needs power most. Enter grid integration, a marvel of modern computing where thousands of sensors communicate in real time with AI-driven control centers, forecasting supply and demand, balancing electricity flowing from sun, sea, and wind so your lights never flicker. Seabirds posed another unexpected obstacle. In Norway, high-resolution radar now tracks avian movements in 3 dimensions. Turbine speeds drop within seconds as flocks approach, resuming rotation only when it's safe for feathered travelers to pass unharmed. Reaching deeper water demanded floating turbines, a feat once thought impossible. Engineers drew inspiration from oil rigs, anchoring platforms to seabeds hundreds of meters below using chains thicker than your thigh. These leviathans remain stable in 10-meter waves, thanks to ballast tanks shifting water instantaneously as ocean swells pass beneath. In pursuit of silence, researchers discovered that blade tips could create ultrasonic noise lethal to bats. The fix? Biomimicry. Turbine edges now riffle like owl wings, reducing noise pollution by up to 90%, while also making them invisible to echolocation. Lightning strikes are an omnipresent threat. Some offshore towers endure dozens each year. Inside their hubcaps lurk braided copper conductors channeling 50,000 amps harmlessly into grounding rods sunk deep beneath the seabed, a split-second ballet between nature's fury and human design. Beneath every visible achievement lies invisible data. Structural health monitoring systems record vibrations. At thousands of points across every blade and tower segment, microcracks are detected early. Using machine learning analysis on petabytes of sensor data, flowing 24/7 from turbine fleets circling the Arctic Circle to equatorial trade winds. Astonishingly, some wind turbine projects collaborate directly with farmers via agri-wind models. Engineers calculate shadow flicker and air turbulence effects, so crops can thrive beneath towers, while sheep graze safely among cables protected by smart fencing that responds only to wildlife intrusion. Not all wind is created equal. Even minor turbulence from nearby hills or other turbines can sap performance. Computational fluid dynamics models simulate airflows at centimeter resolution across kilometers of terrain before a single tower rises, maximizing efficiency for each precise location chosen. If you loved these facts, tap like and subscribe to keep your curiosity smiling with Fact Channels.